Last part of our lesson is on a simple M equals 2 FIR filter design method. So the very fact that it's FIR means that its order, N, is going to be 0. Now, this is not the best type of filter in the world, but it does work, and it's very easy to compute the filter coefficients. And that means it is great to be used on a microcontroller where you can dynamically change what the filter does. You can dynamically change what its cutoff or passband frequencies are. And here's the task. Design a low-pass or a high-pass filter that passes frequencies omega sub p and stops frequencies omega sub s. So just as an example of what I'm talking about, it's not going to precisely pass these things or stop these, but we're talking about something that has a magnitude of a DTFT that looks like either something like this, if it's a low pass. So it passes things up to about here, and it stops things after here. So in other words, if our omega sub pass is less than our omega sub s, it's a low pass. Or we might be talking about a high pass filter. And here, it's going to block frequencies up to our omega sub s, and then it will pass frequencies greater than our omega sub p. So in other words, for the high pass, our omega sub s is less than our omega sub p. And for this particular filter, we're going to assume that our impulse response is FIR, so finite length, linear phase. So since it's FIR, our N has to be 0, our filter order, and we're going to choose our M to be equal to 2 for this one particular filter design. Soon, in an upcoming lesson, we'll talk about how to design any kind of filter, FIR or IIR, of any type of N and any kind of M. But because its M is 2, then that means that its Y of N, its output, is going to have 3 parts to it. It's going to have a part that's proportional to its current input. It's going to have a part that's proportional to its past input, and a part that's proportional to its doubly past input. And we'll scale these things by some amount A, B, and A. So in other words, our impulse response is A, B, A. And since it's a causal filter, this is where our N equals 0. Just to really drive this point home, what we're talking about is it is an A, B, A, where this is going to be 0, 1, and 2. This is N, and this is our impulse response of the filter that we're about to design. Oops, and the last peak is A long. And why does it look symmetric like this? We'll talk about this more in a future lesson, but hand waving a little bit. If the filter instead looked like this, I'm just going to erase this. This is just scratch pad. But if it looked purely even, then can you see how an even H of N corresponds to a real H of Z? And what's the phase of a real H of Z? If it's a real number, the phase is 0. And that's ideal. If it's 0, it doesn't delay your signal at all, doesn't alter the shape at all. That's perfect. So we can't get a causal filter that's purely even, because then it would be non-causal. Then you can see right here for N equals 0, the filter's already responded to things before it's been turned on. So we delay it, and now we get something up here, which would be even, except it's been delayed. Theta of omega, its theta of omega of this thing is going to be equal to minus however it's been delayed. It's going to be equal to this, which is 0, its original one, 0, plus its delay, and it's been delayed by 1, so it's going to be 1 times omega. And so this is going to be linear phase, which is what we want. So I know I hand waved around that a lot, but that's what we're designing. Is this linear phase filter, FIR, and it's a delay of an even impulse response. So we can design this if we just simply can find our A and our B coefficients. I mean, just to be clear, what we're doing is to implement this digitally, we've got our X of N, and we'll delay it by 1. So this is our X of N minus 1. And we'll delay it by, again, so this gives us our X of N minus 2. And now we just sum these guys up. We're going to sum our X of N we'll multiply it by an A, we'll multiply this by a B, we'll multiply this by an A, and we sum all of them up, put in all the arrows so we can see which way we're going, and this is our output. And what I'm representing to you is that if we can just figure out what those coefficients A and B are, we can get a signal. We can design a system that can be a low pass or a high pass filter. So to find A and B, we solve this equation. 2 cosine omega sub p, 2 cosine omega sub s, and 1. So these are multiplied by each other. So this is a 2 by 2 matrix. And you'll predefine what frequencies it passes and what frequencies it stops. And these are the coefficients we want to solve. And this is equal to 1 and 0. So if you put this into your calculators, this matrix becomes a number. This is a variable. These are numbers. You can solve this by simultaneous equations, and this will tell you what your A's and B's are. Now, this is the result, and this is something you calculate in a microcontroller. As this thing is moving, you can have a knob that varies around what your omega sub p is, your omega sub s, and it can figure it out all dynamically. And when your omega sub p is less than your omega sub s, you get a low pass, and the opposite is true for a high pass. I'm going to add one page of theory onto this, just because I think it's really interesting to see how this is derived. I'm going to add one bit of theory onto this, which you're not responsible to know, but I think it's really interesting just to see how it's derived. If you want to stop the video here, you can. You won't miss anything. But if you listen on, I think you'll get a deeper understanding of how DSP works. Now, in order to find this equation, in order to derive it, we need to firstly ask, what again is a transfer function? And we know if it's finite length, it's going to be whatever this value is over here, plus whatever this value is, times b times e to the minus j omega, plus whatever this value is, a times e to the minus j2 omega. Now we can factor out e to the minus j omega here. And when we do that, we get this a times e to the positive j omega, right? Because e to the positive j omega times e to the minus j omega is just a. And then this b stands alone, and this gives us a e to the minus just 1 j omega. Since that a to e to the minus j omega times e to the minus j omega will give us this a e to the minus 2 j omega. Now, what's interesting when we do this expansion is that when we add those two things, we recognize it as being Euler's expansion of a cosine. In other words, the parts underlined in red just become 2 cosine of omega. And then our b is added to that. So now the question is, what we've done so far is we found the DTFT of an arbitrary m equals 2 FIR filter. Now we'd like to know, what is its magnitude? And then what we're going to do is to set that magnitude to either 1 or 0, depending upon if we're in the pass band or the stop band. So the magnitude of this is equal to the magnitude of this, which is equal to the magnitude of the first part times the magnitude of the second part. But the magnitude of a complex exponential is 1. So that's just equal to 2 cosine of omega plus b, since this part is real. Now, in the pass band at omega equals omega sub p, we want the magnitude of our transfer function to equal 1. In other words, we want 2 cosine of omega sub p plus b to equal 1. And similarly, in the stop band at omega sub stop, we want the magnitude of the transfer function to be 0 if it's a stop band. And that just means 2 cosine of omega sub s plus b, we want equal to 0. And now we've got two equations with two unknowns. And if we put those two equations together in a simultaneous equation, we get exactly that matrix on the left. And that's the proof.